In this video, we will be talking about how waves interact with each other and the resulting interference patterns. The interaction between waves, whether they be electromagnetic or waves on the ocean, is called interference. There are two categories of interferences. There are constructive interference and destructive interference. Waves that interact so that they add together to make a larger wave are said to be in phase. This is an example of constructive interference. If you have two waves where the crests or the top of the waves align and the troughs or the bottoms of the waves align, when you add the two waves together, when they overlap each other, the amplitudes add together to make a higher wave or a wave with a larger amplitude. This is called constructive interference. The wave becomes bigger. They construct together to become a bigger wave. And again, we call the overlap of the two waves to be in phase. When they are out of phase, we get destructive interference. So destructive interference have waves that interact so that they cancel each other out and are said to be out of phase. So if we have two waves that are overlapping and the peak of one corresponds to the trough of the other, when we add the amplitudes together, what we end up with is a flat line. This is actually how noise-canceling headphones work. The way they work is you have an incoming sound wave that comes in. The processors in the headphones look to see what the waves of that sound are, and then they put out the wave but slightly out of phase such that it cancels out the incoming wave. What you'll notice is if you're ever wearing the noise canceling headphones, they don't cancel out instantaneous noise, but they cancel out repeating noise. And the reason for that is it takes the processor a bit of time to figure out what the wavelength that's coming into your ear is and process what is needed to be done to spit out the corresponding wave with the amplitude going in the opposite direction. When these traveling waves encounter an obstacle or opening in a barrier that is roughly the same size as the wavelength, they bend around it, and this process is called diffraction. If we had particles, such as down here, particles themselves would not diffract. So one of the key features of any wave is as it's going through something that has a narrow slit, where the width of the slit is approximately on the order of the wavelength, the distance between the two crests of the wave, the wave will diffract. It will spread out in these semicircular fashion from the slit. Particles, on the other hand, if you shoot a bunch of particles towards a wall that has a slit in it, what you will find is that the wall will stop the particles that collide with it, and the particles that make it through will go through unhindered, but will not diffract. They will not change direction. So the diffraction of light through two slits separated by a distance comparable to the wavelength will result in an interference pattern for the diffracted waves. The interference pattern is a characteristic of all light waves. So if we have one slit, the waves coming through diffract. If we put another slit, what we will see is a diffraction pattern. This two-slit experiment is what was done by Thomas Young in 1801 and was the experimental evidence for light behaving as a wave. So when light passes through the two slits, what we find is an interference pattern. This interference pattern, because the waves are being diffracted from the two slits, they come out in these arcs, and at some points they will overlap where the wave of one is going up while the other one is going down. When this happens, they will cancel each other out. So as they come to the wall, you'll actually get these resting places where because of the distance of the two waves, they will always cancel out, and other locations where they will always add together. So you get areas where there is destructive interference, which will cancel the light out. You will see on the wall a dark spot, whereas where they constructively interfere, they add together to give a bright spot. the presence of this pattern is only seen for waves. If light was a particle, what we would expect is, if we have a single light source and two slits, we would expect two bright spots, one that is in direct alignment between the slit and the light source for each one of the two paths. But what is actually observed is this pattern of dark, bright, dark, bright, dark, bright, continuing, and this is only seen in the case of waves. And this is how experimentalists were able to determine that light has a wave-like property.